Hello, I'm going to go over notes 11-4 today. And this lesson, as you can see, concerns the areas of regular polygons and the areas of composite figures. Remember, all of Unit 11 is about areas. And for this one, there's a little bit of vocabulary that you want to know. We've already covered the radius and the center of circles, but now we're going to talk about the radius and the center of a polygon. And it really works best if you draw the polygon within a circle, and then you can see exactly what it's talking about. The center of the circle is also the center of the polygon, and in this case, the center is just point K. And the radius is from the center to somewhere on the edge of the circle. And if we have the polygon inscribed inside the circle, that means any point of the polygon that's got a vertex touching the circle, that is also considered a radius. So here we could say radius kg, so I'm going to say segment kg, or we could really say gk, of course, but we could also say kh. Segment kh is another radius of not only the circle, but also the square. So a square, of course, is a regular polygon, and it's a regular quadrilateral because it has four sides, of course. So yeah, we can call this square inscribed inside the circle, or you could say it the other way around. You could say the circle circumscribes the square. It goes around the circumference of the square is kind of what that means. Okay, so here's one more word that we need to talk about. An apothem is going to be the segment drawn from the very center to perpendicular to one side of the regular polygon. So you're going to draw from the center to one of the sides. In this case, KL is my apothem, and it is an apothem because it is drawn perpendicular to the side GH of the square. So KL is our example, segment KL is our example of the apothem. And we're going to use that apothem quite a bit in this lesson, just so you know. Okay, so moving on, we have a central angle of a regular polygon, and this is really just the same as it would have been for a circle. So it has its vertex at the center of the polygon, and the only difference is, for a polygon, the sides of the angle need to pass through the consecutive vertices of the polygon. So we have a central angle right here, because G goes through one vertex of the square, and then the very next vertex is H. So this angle GKH, angle GKH is an example of a central angle of the regular polygon. Now, what is the measure of that central angle? Well, it really comes down to how many slices are you cutting the circle into. If we really were to cut it into all the slices that you could get four central angles. This is one on the right, you could have one on the bottom, one on the left, one on the top. So n is equal to 4, where n is the number of sides, or even the number of central angles. And what do you do with that n? It's always going to be the same. The number of sides is also going to be the number of central angles. So what do? There's 360 degrees all the way around. We're dividing that 360 degrees by n, which in this case is going to be equal to 360 over 4, which is just 90 degrees. So our central angle has a measure of 90 degrees for a square. Okay, so let's move on. We have some different figures to go over. In example 1, we have a regular hexagon. So it's good to know n is equal to 6 for a hexagon, right? There's 6 sides, 6 angles. Okay, and then here we have it inscribed in the circle, or alternatively you could say the circle is circumscribed around the hexagon. Either way. Identify the center, radius, and so on. So the center, as you can see, is the very center point, which is R. My radius, I can draw a couple ones, RK, segment RK, or segment RL. The apothem is the one perpendicular to one of the sides. The only apothem example I have here is segment RS. And our central angle, again, we only have one. I'm going to just call it angle KRL. And that's our central angle. So what is the measure of the central angle? As we already said, n is equal to 6, so it's 360 over n, or 360 over 6. So our central angle right here, the measure of angle KRL, in other words, is 60 degrees. Okay, moving on. What about an example that's not, it'd be great if we just had a general formula. And we do have one here. If you happen to know both the apothem and if you can calculate the perimeter of your regular polygon, this formula works for any regular polygon. And it's 1/2, the area of the regular polygon is 1/2 the apothem times the perimeter. In other words, yeah, how can we show this? I'm just going to prove this real fast. So notice you can always divide by central angles, and every time you do, you can actually say, I'm creating a bunch of triangles. Over here for the hexagon, I created this triangle. Here I have another triangle. Of course, depending on how many sides there are, the measure of the central angle will be different every time, but you're always going to have triangles. And for any triangle, you know the area is equal to 1/2 base times height. And okay, in this example, I'm going to say, what is my base? My base, I'm going to call it S. And what is my height? My height will be A, because that's A and S. My apothem and my side are perpendicular. So 1/2 base times height, so that's S times A. But that's the area of one triangle, so that's really the area of a triangle. What about the area of the pentagon? The whole polygon, in this case it's a pentagon, you're going to multiply it by how many triangles are there? Well, there would be 1, 2, 3, 4, 5 of them. So it's really 5 triangles, each triangle being S times A times 1/2. So it's 5 times 1/2 times S times A. So keep in mind this is a 5, and this is an S. Okay, what do I do with that? Well, 5 times, I'm going to use some color coding here. 5, and the S, it's really just another way of saying perimeter. So 5 in the S is really just perimeter. So perimeter times apothem times 1/2. So that is the area of a polygon. 1/2 the perimeter times the apothem. And we prove that just by showing with triangles. And that's exactly the same thing we just said, although the order of this is different. They said 1/2 apothem and perimeter, we said the other way around. But yeah, so there's your proof that that formula works. All you really need to know is that it does work, and you need to know that formula. So what about if it was a hexagon instead of a pentagon? So you would find the area of one triangle, and since it's a hexagon, how many triangles are there? There would be 6 triangles formed by the 6 different central angles. So we're going to actually do an example here with pentagons. This time we're not going to be provided, though, with the apothem. We're only going to be told in example 2a that the side has a measure of 4. So what you're probably going to want to do is maybe break that down into triangles that you can do something with. Right triangles are the best triangles to use, and I'm going to redraw that. So what do we have here? We have in a central, what would this central angle be? This would be, the whole thing would have spanned 1/6 of 360. So if n is equal to 6, our central angle, let me get this back on the screen. Central angle equals 60 degrees, but I'm cutting that triangle, this big triangle, in half. So this becomes a 30-degree angle. And of course, we already know that's a 90-degree angle between the apothem and the side. So what's left over here? We have a 60-degree angle. So this is a 30, 60, 90. And also, one more thing, the whole side is 4 meters, and we're splitting it in half. What is the length of this side now, the half side? Just going to be 2. So we can use our 30, 60, 90, oops, I'm talking too fast, 30, 60, 90 table. And remember, it's short side, short root 3, and across from the 90 was 2 times the short. And what do we have specifically for this triangle? We have the short side across from the 30 is just a 2. So that means our long side would be, if s is 2, the long side would be 2 root 3, and then our hypotenuse would just be a 4. And, okay, then what? That means our apothem is actually our long side. So that's 2 root 3. Our apothem equals 2 root 3. And then really the only thing is, well, what's my perimeter? Perimeter, and that's really equal to, we already knew one side was 4, and there's 6 sides, so that's 24. So our area is equal to 1/2 apothem times perimeter. And what does that come out to be? 1/2. We already said the apothem is 2 root 3. Perimeter we just said is 24. So it's a matter of multiplying all that out. And you can do that however you want. I'm going to do 1/2 times 2 is 1. 1 times 24 is 24. And then root 3 was still being multiplied. So our area is really 24 root 3. And we were in meters for one side. So the area must be in square meters.
Okay, I'm just going to edit this part in here. As you just saw, Mr. Margo showed you how to find the apothem using special right triangles, particularly the 30, 60, 90 method. But what I'm going to do is I'm going to show you how to find the apothem using trigonometry. And it also works if you use trigonometry for this example. So this side of this right triangle, this is 2. And I'm trying to figure out the apothem. So I'm going to label that as x. Okay, so what can I do here? I can say that this is going to be my opposite side if I use 30 as my angle of reference here. So opposite of 30, of course, this is the opposite side. And then across from the 90-degree angle is the hypotenuse. And then next to 30, that's the adjacent side. Okay, so then now what I need to do is I'm going to highlight the x and I'm going to highlight the 2. So I have adjacent, I have opposite, or I really should say opposite adjacent, because if we recall, trigonometry deals with sine, cosine, and tangent. So, SOHCAHTOA. And we have opposite, adjacent, so it's tangent. Tangent of my angle of reference, which is equal to my opposite side, which is 2, over my adjacent, which is x. And since x is in the denominator, I can swap places with the tangent of 30, or the x swaps places with the tangent of 30. So I should have x equals 2 over tangent of 30, and then I'm going to get my calculator out, and I'm going to set my calculator to degree, which already is. And I'm going to quit the screen, and I'm going to input 2 divided by tangent of 30, which is 3.5. So x is approximately 3.5. So then what I need to do here is this. To find the area of the regular polygon, it's A equals 1/2 the perimeter times the apothem. So the perimeter, okay, so this side is 4 meters, and these sides over here are also 4 meters. So 4 times 6 is 24, so the perimeter is 24, and I multiply that by 3.5. So the answer is, let's see, I'm gonna put this in my calculator here. So that's so I'm gonna put this on my calculator, and I get 12 times 3.5. And I'm going to compare that to 24 root 3. So 24 times root 3. Yeah, that's about the same thing. So A is approximately 42. Since I'm dealing with area, it's going to be square meters.
For a pentagon, here, notice n equals 5. You're not going to get the same central angle. You're going to get a very different angle. You can calculate it. This central angle here would be 360 divided by 5, which is 72 degrees. The only thing is 72 degrees, even if you cut it in half, 36, that's not a special right triangle. So we're going to give you more information on this one. We're giving you the apothem is 4 and the side is 7. So what's the perimeter? Perimeter is equal to 7 for each side times 5 sides. So it's equal to 35. Perimeter is just equal to 35. And we already know area is equal to 1/2 apothem times perimeter. So it's 1/2. Our apothem in this case is 4. Our perimeter we just said is 35. So multiply this. 1/2 of 4 is really just 2. 2 times 35 is 70. And notice we weren't given any units at all this time around. So we could just say units squared. That's the most proper way to say this. If our side is 7 units and our apothem is 4 units, our area is really 70 square units. That's how you would say it, 70 square units. Okay, so moving on to page 2. Turns out equilateral triangles, it's a 60 degree, 60 degrees, 60 degree angle. So if you split it into 2, you could get a 30, 60, 90. But it's a little bit of work to do that every single time. So what we're going to do is save you from having to do that. The area of an equilateral triangle, if you had S and then you found out this is really, what would that be? That would be half of S. That would be half of S times the square root of 3. You can do all that, but to save you the trouble, we're just going to give you the equation where it's the area is equal to S squared times the square root of 3 divided by 4. Now, so yeah, keep in mind an equilateral triangle and a square, they're both considered regular polygons. n is equal to 3, of course, here. N is equal to 4 here. And you probably already know this one. For a square, the area is really just the side times the side. You could say base times height are both the same, so it's side times side for base and height. And side times side is just side squared. Or you can just remember area is equal to side squared. Either way you want to do it. Okay, so what's the area of this regular triangle, this equilateral triangle? And again, you could do this by splitting it. You could say this is a 30-degree angle because I just split a 60-degree angle, and this is a 60-degree angle. If the hypotenuse is 4, this short side must be a 2, and this must be 2 root 3. And then you could say 1/2 base times height. I now have my height. You could do 1/2 of the whole base. The whole base is really 4, so 1/2 of that is 2 times the height. So that's really going to give me 4 root 3 for my area. Or I can just use that formula that's right above. S squared times the square root of 3 over 4. S squared, I'm going to plug in 4 for S. And that's really equal to 16 root 3 over 4. And area really is just going to be equal to 16 over 4 is just 4. 4 root 3. And we were in feet, so that means we must be in square feet for the area. And if you want to round that off, if you want to round it, put it in your calculator. 4 times the square root of 3 is about roughly equal to 6.9. I didn't do that very well. Let's start over. 6.9 square feet. Either way, this is the exact answer, and that is the approximate answer right there. Okay, well, how about this one? It's a square, and the half diagonal is got a measure of 7 centimeters. So, of course, here's another 7. And it would be great if we just knew what kind of triangle we're dealing with here. Remember, this is a central angle, and what is the measure of that central angle? 360 divided by 4, because n is equal to 4. So that is a 90-degree angle. 90 degrees, which means if this is 7 and that's 7, this is really a 45, 45, 90. 45, 45, 90. And that means if that's 7, 7, this must be 7 root 2. Leg root 2. Okay, so then what? 7 root 2 is actually equal to our side. And we know area is equal to side squared. So area is really equal to 7 root 2, the whole thing, squared. How do you do this? I would do distribute the squared to both. I would say it's 7 squared times the square root of 2 squared, which really gives me 49 times square root of 2 squared is just a 2. So my area is equal to 98, and we were in centimeters, so it's square centimeters. Okay, moving on to the next example. Example 3. This is what we call composite figures. Composite means you're putting together 2 or more figures to make a bigger figure, a different, unique figure. So what do we have? We always have basic building blocks, kind of like you're putting Legos together. Here we have a triangle on the upper left, and we have a rectangle on the right. So to find the area of the whole composite figure, we need the area of the triangle plus the area of the rectangle. Well, what is that? The area of the triangle is 1/2 base times height of the triangle, mind you. And then the area of the rectangle. A rectangle is really just like a parallelogram. So we can say length times width, or base times height, however you want to say it. but the base of the triangle and the base of the rectangle are not going to be the same. So we're going to just stick with length times width, because that's how you learned it before when you were younger. Anyway, 1/2 base times height of the rectangle. So notice this rectangle goes 12 across from here. And this whole top of the composite was 20. So what's left over here? We have 8 left over. 8 plus 12 makes up our whole 20. And do we now have enough information? We know this is 10 going down for just the dotted line. Another 15 over here. So if we add all that up, the whole right side, or even the whole left side of the rectangle, is 10 plus 15 is 25. Okay, so coming back to our rectangle and triangle. 1/2 base times height. What is my base and height? I'm just going to say my base of the triangle is 8, and my height is the 10. The length and the width of the triangle, I'm going to say my length is the up and down part, which is 25, and the width, I already said, is just the 12. You got to be careful on these. So what does that come out to be? 1/2 of 8 times 10 is just 40, and 25 times 12 is 300. So the rectangle has a lot more area than this triangle, and that kind of makes sense because it's much bigger. So the total area is equal to the sum of that, which is 340, and none of these had units, so I'm just going to say 340 square units. We have 2 more composite figures to go. This one on the right is actually pretty similar in that we have the area of the rectangle and the area of the triangle. I'm just going to write the same formula. Area of the rectangle. And again, same formula. 1/2 base times height and length times width. So length times width. And the only question is, well, what are they? Notice we had the height given for the triangle, which is pretty helpful. And the base of the triangle is really the whole vertical part of the rectangle. So it's just 1/2 the base of 62 times the height of 27. And then for our rectangle, our length, let's just go with 62 again, times our width of 54. So the only question is, well, what is that? 1/2 of 62 times 27, that is 800. I can't do that, actually. Let me just check my work. 1/2 times 62 times 27. So I get 837. 837. And for the other one, I get 62 times 54. That's 3348. So our total area is equal to the sum of those two, which comes out to be 4185. And again, no units were provided, so we're just going to say a generic square units. Finally, we have one more composite figure, and this is a semicircle, and we have let's see, what else? We have trapezoid. So we have area of trapezoid plus area of 1/2 circle. I'm just going to get started with something for that. Well, what is our trapezoid? We've already covered trapezoids. We know this whole top base is 2 feet, the bottom base is 4 feet, it's got a height of, what was that, 7 feet. So let's say 1/2 the top base plus the bottom base, and I don't know why I put that so small, times the height of 7. Sorry, I was going to do something different. 1/2 of 2 plus 4 times 7. And then let's just go ahead and do that. What's that? 6 times 1/2 is 3. That's equal to 21. 21 square feet for the trapezoid. And that circle, it's actually a semicircle. So whatever the area of a circle is, it's going to be half of the area of a circle. And what is the radius, since we do need radius? If the diameter is equal to 2 feet, the radius is equal to 1 foot. So that's equal to 1/2 pi times 1 squared, which is really just equal to 1/2 pi. And that is also in square feet. So 21 square feet plus 1/2 pi square feet. And if you do add them up, this is about 1.57. So the total area is 1.57 plus 21, which is about 22.57 square feet. And that is our third composite figure. So notice composite figures, you're just breaking them down into smaller pieces. We had a trapezoid and a semicircle. And for the other two, we just had a triangle and a rectangle. So you got to find the individual areas and be sure to add them up at the end. If you forget, then you will not get the right answer.
Hey, we actually fooled you. This is actually the last problem of today's notes. You're given an equilateral triangle, which we call it AED, and you have a square ABCD, where we say that AD is 2 inches. So, your goal here is to find the area of the shaded region. And note, we have 2 figures here. We have a square, and we also have an equilateral triangle. So, given a square, ABCD, and AD is 2 inches, well, that's really, really easy. I can figure out the area of the square using this formula, A equals side squared. So, let's find the area of the square. So, the area of the square is equal to side squared, or 2 squared, which is 4 inches squared. And to find the equilateral triangle, let's do that. So the area of the equilateral triangle is equal to this. Side squared root 3 divided by 4. So s squared root 3 divided by 4. We already know what s is. It's 2. So it's 2 squared root 3 divided by 4. And I can go ahead and simplify this. So I have 4 root 3 divided by 4. And I can simplify that even more because we have 4 here, 4 there. They cancel, so I'm just left with root 3. Okay, so now what I need to do is I have the area of this square, and let's say that this equilateral triangle erases part of that, shading there. So I have this white space here. It's basically shaded minus unshaded. So shaded minus unshaded. That's how you find the area of the shaded region. Shaded minus unshaded. So the shaded region is the square. It's 4 inches minus the unshaded, which is root 3. So if I put into my calculator, 4 minus the square root of 3, the area is approximately 2.27 square inches. And that's your answer. And we're done with the notes. Toodaloo.